Welcome back. Let's go now to the next exciting part, which is Apache Spark right here. Notice that this is kind of called the same, massive parallel processing, just part 2. It's in fact the next generation of MapReduce. It's like Star Trek, the original series, and Star Trek, the next generation. It's the same idea. MapReduce is 20 years old. It was invented at that time, having in mind downloading and indexing the internet, right? One of the primary use of MapReduce was to index the web and build an index and a search engine. But since then, things have evolved. And what happened is that a lot of people realized that their problems were a bit more complex than a single MapReduce job, and they started using MapReduce in a chained way, meaning that it's a chain of MapReduce jobs. But the problem is that people had to do it themselves because MapReduce only works at the level of a job. So there was a lot of manual additional work in order to execute a chain of MapReduce jobs. An example of that is matrix multiplication that you can do on top of MapReduce. In fact, with machine learning, this is what we do, and we have to iterate. And at some point, it became so inconvenient that some engineers said, we need to re-engineer the whole thing and come up with a more abstract and even more generic system that takes care of it so that people no longer need to do it. This is Apache Spark. There are many others now that do the same, but again, if you know Apache Spark, you will have no problem understanding the others. So let's get into it then. First, where are we? This is the stack. That's what we've already done, right? We've already covered half of it. Now we are in the middle of processing, and there's a few more things that will be left at the end. Last week, well, more precisely, the last recording, we've looked into MapReduce, and a MapReduce job is really map, shuffle, reduce, finished, right? That is one MapReduce job. We've looked at the infrastructure. We've seen it's exactly the same architecture with a coordinator node and worker nodes. The name node also runs the job tracker, and the data nodes also run the task trackers, which you cannot see in the lecture hall because of the toolbar that is hiding it. There you go. So the task tracker, which are responsible for hosting the slots that run the map and reduce tasks. Now you know what they do. But now if you look at this architecture, this was actually called version 1 of MapReduce. That's the initial architecture of MapReduce. There's a few problems with that architecture. If you look at the job tracker, this is the brain over there in the coordinator node. It has to deal with resource management. It has to know what CPU cores and memory is available, with scheduling the tasks over the slots, about monitoring. If something fails, you need to restart it and so on. The job life cycle, fault tolerance. Again, imagine that during the map phase, one of the map slots crashes, then you just ask another CPU core to run the same task again, right? So this is called fault tolerance. So this kind of works automatically. The problem is that this job tracker has too much on its plate, right? As we say, jack of all trades, master of none. So it has too much responsibility. The problem is that it's a single machine that has too much responsibility. So this is the first problem that the engineers tried to solve. It's associated with consequences, actually. One of them is that when they tried to use this first version of MapReduce, they managed to make it run on clusters of up to 4,000 nodes, but then it started not working anymore. And again, 40,000 tasks, it means roughly 10 tasks for every node, right? But it didn't scale beyond that. So that was causing a bit of issues. The second issue is, again, that's the bottleneck, because all of these responsibilities are on the same machine. So if at some point it starts to be overloaded, then that slows down the whole cluster, right? So this is a bottleneck. I'll come back to bottlenecks in a few weeks. And it both schedules and monitors. It's both responsible for saying which task gets executed where, of assigning them, and also of monitoring for crashes, of seeing if a task is done, and so on. So it has too much. You remember this node slot task function that I told you about? The problem here, there's also a problem here, is that we have to know before we start the job what slot is for reducing and what slot is for mapping. But do you see the problem? First, it's a fixed size. You have a fixed number of slots for mapping, a fixed number of slots for reducing. But the other problem is that during the map phase, only the map slots are actually doing something. The reduced slots are just doing nothing. They just have to wait, and that's it. So you're basically wasting a whole part of your cluster doing nothing. And then the opposite in the reduced phase. In the reduced phase, it's the reduced slots that do the work, and the map slots will have nothing to do anymore. So you see, it's kind of not optimal, because we would say in technical terms the non-fungibility of the map and reduce slots, right? They are fixed. We have a question in the Zoom chat. In practice, yes, but that's what I'm coming to, because we are going to solve that problem. And this is exactly what's going to happen. We are going to use the other type of slots. Basically, what I'm describing here is version 1 that had this issue. And this issue was solved exactly in the way that you just said. It's that we are going to no longer have this problem of idleness, and we will use all of the available resources. Right? So the intuition is correct. Again, that's just version 1 that I'm talking about here. Okay. And thus, we have a solution to this problem called YARN. YARN means yet another resource negotiator. As soon as you have a technology that starts with YA, it's probably yet another followed by something, right? So yet another resource negotiator, just like yet another markup language, YAML, that you already saw. Yet another resource negotiator fixes all of these issues. What is the architecture of YARN? You guessed it. It's again the same centralized architecture with a coordinator node and worker nodes. We just need to find new names for them. So for the coordination node, it's called the resource manager. And the other machines are called node managers, right? So what we have in YARN is the notion of container. A container is a little bit like a virtual machine, kind of, sort of, right? So a container is a bunch of resources on a machine with so and so many cores and so much memory. For example, 4 cores and 16 gigabytes of RAM, but you might have multiple containers on the same machine. For example, if you have 16 cores, you could have 4 containers of 4 cores each, and so on and so on. So this container thing is the way to manage the resources. If you know of Borg or Kubernetes and so on, it's kind of a similar idea, but on a very, very low level of resources. So this is the abstraction of YARN. We have a node manager on every worker node, and we have a resource manager, and we abstract away the resources in CPU and in memory as containers. And the idea is that when a client connects to the cluster and wants to execute a job, for example, a MapReduce job, but it could also be Spark or any other technology, what happens is that the resource manager, who is more clever than the job tracker, is going to accept the job and immediately delegate to somebody else, right? It's like if some of you become managers in the future, you delegate, right? So the resource manager say, yes, I accept that job, but somebody else is going to take care of that. So what the resource manager does is that it requests a container here, promotes the container to an application master, and it's the application master that's actually going to take care of the job, right? So you see how now we split the responsibilities. Now, the resource manager doesn't need to care about the monitoring of the job and so on. It only needs to care about the containers, right? And so now what happens is that the application master kindly accepts the responsibility of the job, and it says, yes, but I cannot do it alone. I need help from other containers. So it immediately connects back to the resource manager, requests help from more containers, gets them allocated, and then you have everything nicely executing on this machine. And you see that in the execution of the job, the resource manager is no longer here. It's purely the application master and the containers, right? For whom does that make sense? Yes? I'm not sure if it's going to work, because yeah, go ahead.
Order in which the red containers are chosen by the resource manager?
So you're asking about the order in which they are allocated. It's not part of the material of the lecture, but I can briefly say a few words on that. In fact, I am going to explain a little bit. The idea is that this cluster is not only used by the clients. Imagine that it belongs to a company, and let's say there are hundreds of users of the cluster. It means that you are running these jobs concurrently with other people. So Yarn has this way, it's based on game theory and so on. It has this way of smartly allocating the resources. Maybe you are entitled to a certain share of the cluster, and then it will prioritize you on these shares of the cluster. So it's basically dynamically allocating the containers, but if there are too many people at the same time, it might tell you, wait, you're now fully utilizing your share, some other people need it, or it's going to say, oh, many other people are not even here, so I'm going to give you some of their share. So it's something dynamic. The details of that are very complex. I used to have them in the lecture, especially in the master's lecture, but in the end, we dropped it because it's really more a physical level, and I didn't want to distract away from the big data part. But it's a very good question, and that's really something that happens dynamically. When I said game theory, it's because the system is designed for people not to cheat, meaning that when you request your containers, you have an incentive to really request what you want and what you need, and not over-request or overuse the cluster, right? Did it answer your question? Yeah. It is part of it, indeed. So I'm repeating because people don't hear you on Zoom. There is the notion of proximity and distance between the containers, and you also try to allocate in such a way like to respect the distance and let's say be location aware of the distance between the containers, right? It's just not part of the material, basically, but it's interesting to know these things, right? Yes, there is another question over there. We can try with the box. Otherwise, I can also repeat what you. Let's try, and I give a bit of volume.
How do we know if the node manager is working? If the resource manager is no longer taking care of the monitoring?
How do we know if the resource manager is?
If the node manager is still working, so like if it wants to keep scheduling jobs and stuff like that, how does it know if it's alive, if it no longer takes care of the monitoring?
So yes, indeed. So the resource manager knows if they are alive with heartbeats. It's exactly the same principle as in HDFS. So basically, all of the node managers, they are going to send heartbeats to the resource manager, and the resource manager is aware of losing nodes or crashing nodes and so on. It's just that the responsibility of rerunning, for example, a map task somewhere else, that's going to be the application master now that takes care of that. The resource manager still wants to know which nodes have a problem so that it does not allocate the containers there. And yes, you're absolutely correct that there is a heartbeat and a way of communicating that, right?
Thank you.
Thank you. Okay. So what are the resources we're talking about? Memory and CPU mainly. There is work in progress to also consider the disk usage and the network, but today it's more like memory and CPU are the two we really look at. What's important is that at the same time, you might have plenty of jobs running on the same cluster. Think a company-wide cluster with hundreds of users. Maybe there are 20 MapReduce jobs executed at the same time and 30 Spark jobs and so on and so on. And so we have as many application masters as jobs, okay? But only one resource manager. Now, and this is the question you ask, we indeed have communication between the node managers on the right and the resource manager on the left, where the node managers communicate their resources. They say, I have that and that many CPUs, I have that and that much memory, and I'm alive, right? Every couple of seconds, you send a sign of life. And then the resource manager keeps a list of the nodes that are valid, that are working, and those that are not working, and this you cannot use to allocate resources. The resource manager does not monitor tasks. That's the job of the application master, right? It's not going to restart map task or restart the job upon failure, right? That's not going to happen. The application master is also application specific. There is something for MapReduce, there is something for Spark and so on. So Yarn is fully agnostic of the technology you're using. It doesn't care if it's MapReduce or Spark or anything else, right? It's fully general. It's the job of the application master, the crown here, to monitor for a failed task, for example, a task that failed, and relaunch it with some other container, right? That's the task of the application master. I just have a few slides because, again, I barely explain it anymore, but when you schedule the containers, you need a strategy, right? How do you schedule the resources? A very naive approach is FIFO, first in, first out. It means somebody uses the entire cluster, and when they're done, somebody else uses the entire cluster, and when they're done, somebody else uses the entire cluster. Now, as you can imagine, this is not how it can work at the level of a company, because you cannot have the whole company wait for a single person to complete. So in practice, what you do is that you assign, maybe in some company C-level suite meeting, who gets what share of the cluster, basically a money thing, who gets what share. And so here in the university, let's say the departments, they decide that the mathematicians get 40%, the physicists get 10%, and so on. And this is kind of the guideline for the use of the cluster. And then the resource manager will keep that in mind to allocate. For example, it can have queues. There might be a queue for the math department and a queue for the computer science departments. But then they will really preserve the resources and have them for the exclusive use of a department. And then within the department, you're going to have a succession of users that need to wait for each other, right? So this is another strategy called the capacity scheduler. And we even have a fair scheduler. The fair scheduler it's been published, I think, at Stanford as dominant resource fairness. It's a very good paper. The idea is you have some elasticity. If the mathematics department is not currently using the cluster, then why would you block that part of the cluster unused, right? In that case, you elastically redistribute it to everybody else. And the fairness is basically the idea that you fairly allocate based on the memory and CPU needs of everybody. We have a helicopter for those on Zoom who just passed, okay? So this is, you don't have, again, that I just have a slide to explain, but this is very, very high level. The difficulty that they solve in this fair scheduler is that if you allocate the cluster just based on a single dimension, like you only look at the cores or you only look at the memory, then that's easy because it's easy to know what it means to use 40% of the cluster and so on. The problem appears when you have multiple resources. You have the memory and the CPU. And imagine that Alice from the math department uses containers of 30 gigabytes and 2 cores, and Bob from the computer science department using containers of 10 gigabytes and 6 cores. How do you deal with the discrepancy, right? Because Alice is more memory intensive and Bob is more CPU intensive. And so this dominant resource fairness has a smart way of dealing with this kind of situation and of telling you, Alice is going to get that and that many containers, and Bob is going to get that and that many containers, right? Some of you who are interested, as an optional read, you can read the dominant resource fairness paper. There's some game theory inside also. But again, I'm not spending time on that. This is just for you to know that there exist algorithms and techniques that deal with memory and CPU to fairly allocate them across the users, right? So in that case, basically based on the fact that every container of Alice, you look at the maximum percent. So here it's 3%, that's the memory. For Bob, it's 6% because it's CPU dominated. And basically because Alice's number is 3 and Bob's number is 6, assuming in the company meeting they are allocated half of the cluster each, the intuition is that Alice should get twice the number of containers compared to Bob, because her containers are twice as small as Bob containers, if you consider the maximum resource. So for example, Alice would get 20 containers and Bob would get 10. And then you see they both get 60% of the cluster for their dominant resource, which is fair. Again, parenthesis closed, you don't need to understand that. This is just to say that there are very smart people who manage to find strategies to allocate the resources. And so the result of that is that now you can have these company-wide clusters with people doing all sorts of things with that. Some people might be doing MapReduce, some others, some Spark. That's what I call DAG distributed processing, that would be Spark. message passing interface, MPI, graph processing, machine learning, training an LLM, on the same cluster. And Yarn is taking care of fairly distributing the resources to everybody who is using the cluster, right? This is what it's about. So we separate between scheduling and monitoring because now the scheduling is done by the resource manager, but the monitoring is delegated to a container that's called an application master. It's scalable, so now we can process more data than we could with the first version of MapReduce. It's well available because you don't block the cluster unnecessarily. You don't have the bottleneck of the job tracker anymore. And it's multi-tenant, meaning you can have many people using the same cluster at the same time, right? Okay. So this is Yarn. That was just a very small parenthesis on resource management. So what happened is that after Yarn was invented by the engineers, then came MapReduce version 2, which is the same logical interface to MapReduce, except that now instead of the job tracker and task tracker, it's running on Yarn, right? But the look and feel is exactly the same. It's just running differently, but it's exactly the same MapReduce, the same map function, reduce function, and so on. But now, since we have Yarn, during the map phase, we are not going to be using any idle reduce slots that are doing nothing. You will only allocate the reduce slots at the very last minute when you need to actually start the reduce phase. The application master will request the resources for the reduce slots only when it needs them. So it's more efficient. For whom is that clear? For whom is that not clear? For whom is that clear? Okay, thank you. So introduction to Spark, that's the next level. So now I'm coming back to the logical level in terms of the way we use it. MapReduce, if I want to be a bit provocative, I'm going to call it map shuffle map, because if you think about it, what's the difference between reduce and map? Reduce and map are just some parallel phase, right? So you can look at it like a map followed by a shuffle followed by a map that happens to be dealing with a reduce function. Now, that's very specific, and the problem is that then people need to chain plenty of MapReduce jobs one after the other, and that's a lot of work. If I zoom out and put it like this, we basically have this input data set that is mapped to an intermediate data set that is reduced into an output data set. Well, Spark basically generalizes this to any graphs. So instead of having specifically just a map and then a reduce like this, chains, you have a fully generic graph of data, and you just let the data flow, and you can do multiple things with the same data set. It's not any graph, it's a graph that cannot have cycles, right? A directed, a cyclic graph. It just means that if you follow the arrows, there has to be a flow top down. You cannot go in circles across the arrows multiple times, no cycles. So this is Spark. This is the new thing about Spark, and that's extremely powerful because now you no longer need to chain the MapReduce jobs anymore, because you can just do it within this new paradigm with a graph. So this is why we have Spark. A bit of terminology. You know that in every technology, it's like I said multiple times, when you have a hammer, everything in the world looks like a nail. In MapReduce, everything is a key-value pair. In Spark, everything is an RDD, a resilient distributed data set. So the RDDs are kind of the key-value pairs of Spark, if you want. So what is an RDD? A resilient distributed data set. It's a very scary term, but it really means that it's just a big collection of whatever. Collection of records, a collection of strings, a collection of whatever you want. It's a big collection that is partitioned. So it means that you could have a collection with billions of whatever, and these billions of whatever are spread all over the cluster. Maybe there's on 1,000 machines, on every machine, there is 1,000,000 of whatever, right? I on purpose say whatever because it can really be anything. So an RDD, now if you come back to the name, distributed basically just means that it's partitions across the cluster. And resilient means that if there is a crash somewhere, it's automatically recomputed. So if you lose part of it, Spark is automatically going to figure out and reconstruct it for you. So this is what we call resilience. So again, an RDD is just a big collection of whatever. That's one thing to remember. And that whatever doesn't have to be a key value. That's the new thing. In MapReduce, it's a collection of key values, has to be key values. In Spark, it's really a collection of whatever. It can be key values if you want, right? You could have a collection of key values, but you could have a collection of integers, you could have a collection of JSON objects, you could have a collection of pictures, you can just have a collection of whatever you want. It can even be a heterogeneous collection, by the way. All right. So the RDDs work like water. There is a cycle. Just like water evaporates from the sea and then forms clouds and then rains and so on and so on, RDDs work in the same way. They have a life cycle. It all starts with the creation of an RDD. How do you create an RDD? Well, that can be read from HDFS. You have some data sets stored on HDFS, and then you say, okay, make an RDD out of that. And maybe it's, I don't know, maybe it's a collection of JSON objects stored on HDFS, and you load it as an RDD that's a collection of JSON objects. Or it could be, I don't know, a relational table. Then you just create an RDD of records, an RDD of rows, right? So it works from HDFS, from S3, from Google Cloud, from Azure. It also works from your local file system. In fact, you can also create an RDD from your laptop. That would also work, and you can even do it on the fly. On the fly means in Python, you create a list in your memory and you turn that list into an RDD, right? It's technically the same. It's still a list. It's a collection, but now it's an RDD. That would be on the fly. So you can create RDDs. Once you have created an RDD, you can transform it. Transforming an RDD means you create another RDD out of the first one with some transformation. That transformation could be mapping, could be reducing, but it could be many, many, many other things. In fact, there's a whole restaurant menu of transformations that are at your disposal. So it's more generic than MapReduce. So we can transform an RDD into another RDD in this way. And then at the end of the life cycle of an RDD, we have an action. An action takes an RDD and does something with it. What can you do with it? Well, maybe your RDD is small enough that you want to print it on your screen. Right? So this is one way in your Jupyter notebook. For example, you can just print your RDD if it's small enough. You could also download it to a Python list. For example, it's an RDD on your cluster, but you know that it only has 1,000 values. Then you just download it and have a local Python list with your 1,000 values. That's also an action. The action could also be write it all back to HDFS. Right? Imagine you have an RDD with 1 billion values. There is no way you can download that. It's too big, right? So instead, you're going to instruct Spark to write it all down to HDFS in parallel, and then you're going to create a directory with 1,000 files that is going to contain your RDD. It can also be downloaded to your local file system, but again, for this to be safe, you need to be sure that the RDD is small enough, right? Because if the RDD is too big, it's going to crash your machine. So if you know the RDD fits on your machine, then you can also store it on your local file system, write it back to the local file system. Okay? So you create RDDs, you transform RDDs, and you act on RDDs at the end. So basically, the whole way it works in Spark is that you have this graph of RDDs that depends on each other. The ones at the top are the ones that get created from HDFS or any location, and then you transform and transform and transform RDDs. You can even have transformations that take multiple RDDs. In that case, you take 2 RDDs and maybe you combine them into another RDD. That you can also do, right? You can use an RDD for several transformations, right? You could not do that in MapReduce. Who sees that it's more general than MapReduce? Right? Awesome. So it's more general first because it doesn't restrict to key value pairs. You can even just have values, not necessarily key value pairs. Second, you have a general graph like this. It doesn't have to be just map and reduce. You can have any directed acyclic graph. Third, it's more general because you can also have dozens of different transformations and not just map and reduce. Next week, I will show you the full restaurant menu of transformation. There's many, many, many of them. It's like a catalog, and then you pick from that catalog in order to build your graph. right? So that is the logical level of Apache Spark. It's extremely powerful. It's very popular too. Very appreciated. A lot of people use it. Just before you go, if I have a chance to check. If you've been following. Who is reading the textbook, by the way? Who already read the chapter on MapReduce? You should read it, right? It's complementary to what I'm saying. And there is also a chapter on Yarn and a chapter of Spark. So don't hesitate to read it. It's an opportunity to go over the material one more time, but at your own pace. So that tells me to slow down a bit, which I will do next week. Yeah. So come with questions next week. Anything that's unclear, come to me and we'll start the lecture with that, right? So I'll make sure to touch base with everything we've covered, and then we are going to take it from there. Okay. That also reassures you, because if you felt like you didn't get everything, then you see you're not the only one. So that probably also gives you a better feeling. All right. So again, read the textbook, do the exercises, and next week I'll slow down and we'll make sure to consolidate everything we've learned. Thank you very much. See you next week. Don't forget to fill the VGates form as well, etc. Enjoy the exercise session, and thank you for the moderation. Goodbye.